Rock, paper, scissors is famously a not very interesting game, mathematically speaking. Yes, there are some interesting nuances. It's a non-transitive game. Oh, look at that. There is no one best strategy. But after you've played a few rounds, you realize that it's basically, unless you're doing something really fancy psychologically speaking, there's no particular benefit, there's no advantage to each person, there's no strategy to it. Except, I suppose, one small person of my acquaintance has found a trick that works surprisingly often. You pause briefly after your opponent reveals their hand before you show your choice, which gives you just enough time to make the right decision. Interestingly, that strategy is not a million miles away from this variant of the game, which I find a lot more interesting. The game is called Rock, Paper, Scissors -1. I saw this while playing Roblox with my son on a game called Decide or Die. You get to decide before you show your hand. You get to show two things. One is the thing that's going to be your final choice. The other is something else. So you still have your three options to choose from. Of those three options, you're then going to pick a couple of things that you're going to reveal to your opponent. And the rule is, after you've revealed those two things, you're going to pick from those two things for your final step. So it's kind of two rounds going on. The first part is you show two things, and the final step is when you make your final decision. So let's see how it plays out. If these two players both put down two things, Prof has gone with scissors and paper. Noob has done something a little bit silly here. If we're going to have one which is going to be your final hand and one which is a red herring, it seems a bit pointless to use the same one for your red herring. Now Prof knows exactly what Noob is going to do, and it's fairly easy to see what he should do in response. If he went with paper, he'd definitely lose. If he goes with scissors, he's definitely going to come out with a draw. So let's back it up a bit and think carefully, because this is going to be the first basic strategy that you're going to want if you're going to plan to own this game while you play against your many friends. The first thing that you don't ever want to do is play the same thing twice. You basically lose all choice and flexibility for the final round, and now all you can do is watch what the other person's about to do, and they're either going to beat you or you'll draw. So neither of those are great for you. In fact, this was about the best you could have hoped for. You had scissors and scissors, and you just got lucky that Prof hadn't chosen rock as one of his two options. He was choosing 2 out of 3 options, so actually of his choices, 2 of them involve rock. He could have gone rock, scissors, or rock, paper, in which case he could beat you straight away. The fact that he's gone scissors, paper means that you're lucky to get away with only getting a draw. So what if both people play 2 different things? This is the next thing we need to investigate, see whether there's any sneaky strategies lurking under the hood with this one. Now, the first thing to notice is if you play 2 different things, they won't be completely different from the other person's, because there are only 3 things to choose from. I can't choose 2 of them and then you choose a different 2, because there's going to be some overlap. But what if they completely overlap? It might be that I choose scissors and paper and you also choose scissors and paper. Okay, well, at least you're not doing any worse than me at this point, but it makes for a fairly dull game, because it's pretty obvious that no one's going to choose paper, because all they can do with that is lose, or potentially draw if both people are silly enough to go with paper. So you pick the dominant option and you should be fine. You'll get a draw, but you're going to want to play again and see if you can find a more interesting scenario. This is another one of those little edge cases we need to rule out. We don't do the same thing for both of our options, and if you end up happening to draw the same 2 as the other person has drawn, then just pick the dominant strategy and you should be fine. You'll walk away with a draw. This is the most interesting of the different scenarios. This is the one where you've really got to start thinking, and if you think too hard, you end up taking yourself in circles. Let's investigate this one. There will be at least one option in common, so there is a difference between Prof and Noob in terms of which one has the best chance of coming out of this kind of exchange on top. I would recommend at this point you pause. If you've not played this, or you've not thought about it yet, have a little think about which of these 2 people you think has the advantage. If we played this over and over again with exactly the same choices at this stage, which one do you think on average would come out on top? And how do you think they would guarantee that? What would you do if you were Prof? What would you do if you were Noob? When you've had a bit of a think, let's move on and look at the next bit. The first thing I want to highlight here is actually mathematically there are only a couple of different things that can happen, and they're all basically the same at this stage. If we've ruled out the possibility of going with the same option twice, and we've already considered what happens if you are both got identical choices, then you're in one of these scenarios. Either you've got scissors and paper and I've got paper and rock, or you've got paper and rock and I've got rock and scissors, or finally you've got rock and scissors and I've got scissors and paper. There's a cyclical nature to this, and although I wouldn't say the two players are equally likely to win, as we'll see in a minute, it is definitely true that it doesn't really matter if it's scissors versus paper versus rock or paper versus rock versus scissors. That cyclical thing means we don't need to investigate all three of these options. We just need to pick one arbitrarily and work with that. So that's what we're going to do. We're going to put things in a table. This is going to help us to clarify exactly what happens in the different situations and talk through what the different players might do to improve their chances of winning. This particular table is one that Prof has created, so it's his own payoff matrix, if you want the fancy term. It just means it's going to tell Prof what kinds of gains he gets from each of the different situations. If we put a 1 in there, it means he wins in that situation, a -1 means a loss, and 0 means a draw. If they both go scissors, it's a draw. If Noob goes scissors but Prof chooses rock, he's going to win, and if Noob goes paper and Prof chooses scissors, he also wins. And the final option, Prof goes with rock and Noob chooses paper. In that situation, Prof loses. It should start to be clear now why Prof is in a better situation. So if you were looking at the previous slide and thinking, yeah, I reckon I'd rather be Prof than Noob, well, you're on the right lines. There are more ways to win if you're Prof, and there are fewer ways to win if you're Noob. So he's definitely got what looks like an advantage, but is it really an advantage? And is it even an advantage that he can exploit? Can he actually make something out of this? Or is it just something that looks promising on paper, but Noob can easily block this particular thing? Let's think about what you would do if you were Prof. Perhaps you're thinking, I go scissors, it's the safe option, right? If I go scissors, I might win if he goes paper. At the very least, I'll draw when he goes scissors. Yeah, fair enough. However, you're not going to win if he also plays scissors. So it doesn't seem like a strategy for winning. It's a strategy for not losing. It's the play safe strategy. It's the, oh, I don't know, if I put my money in this investment or this investment, maybe I might lose money. Yeah, and maybe you might gain money, and you don't know for sure. So instead, you don't invest in anything and you just keep the same amount you have. It's a valid strategy, but it's not going to gain you anything. And if you've got an advantage, you want to try to take advantage of that advantage. So this is the question. Prof has got a win or a lose if he goes with rock, and he's got a win or a draw if he goes with scissors. Noob is a win or a lose versus a lose or a draw. Those are his two choices. It feels like it's worse. I'm pretty sure we'd rather be Prof, but let's see if we can figure out why and whether there's any way Prof can benefit from the potential advantage he seems to have. Firstly, there is no clear dominant strategy. There's no obvious place that Prof can sit and say, if I do this, this is definitely going to work for me. If he decides he wants to use rock, then there's a chance he'll lose. And if he goes with scissors, then there's a decent chance he's just going to keep drawing. Let's think about it game by game. Imagine we start out in this situation where Prof and Noob are both playing scissors. Okay? And notice that Prof's best move kind of depends on what Noob does. So we're both playing scissors. That means although Prof is getting a draw every time, he's now starting to think, well, Noob keeps playing scissors, maybe I should play rock. So he throws in a rock. And that suddenly means that he's going to be winning. As long as Noob keeps playing scissors, Prof can start playing rock and he starts to win. What's going to happen next? Well, Noob is not very happy with the new situation. He's losing every single time. So he's probably going to do the only thing he can do, which is switch from playing scissors every time this game strategy version comes up to playing paper. If he plays paper, Prof starts losing if he continues to play rock. What does Prof do? He starts playing scissors again. And if Prof plays scissors, then Noob is going to start losing once again because Noob is currently playing paper. What does Noob do? He's probably going to go back to playing scissors. Now you could chase each other around a loop like this, and one of my son's suggestions was that you just have to think a couple moves ahead of your opponent. So if they've thought this through a step or two in advance, you think 3 steps in advance. I feel like that strategy is going to take you on a bit of a chase your own tail kind of thing. However, it's not dissimilar from the actual optimal mathematical strategy that I painstakingly came up with. And in fact, when I attempted this strategy against him, he was doing very similar sort of thing, slightly different the way he approached it, but he ended up getting the better of me anyway after our 20 or so games that we played. So whatever he's doing in terms of chasing this cycle around is very similar to what I ended up doing by computing the game theory optimal strategy. Let's see what that looks like. We're looking at what's called an unstable game. There's no single best move. So a game theorist, mathematician would look at it and say, if there's no single best move, is there a move that I should be playing more often than another one? And we create something called a mixed strategy. The really nice thing about a mixed strategy is if we do it right, we don't care what our opponent chooses to do. We don't mind if they've got a fancy strategy, or if they're flipping a coin, or if they're always going with paper, or they're always going with scissors. None of that will bother us because we've chosen a strategy that doesn't rely on knowing what they do at all. Let me show you what that looks like. First of all, Prof is going to choose randomly, but not randomly in the sense of flip a coin and go 50-50. Randomly, but not necessarily equally. We're going to say the probability of going for scissors, we're going to use P. So if P is 0.8, it means that 80% of the time we choose scissors, and therefore 20% of the time we choose rock. Okay, maybe P is only 0.1, so we're going scissors 10% of the time, and we're going rock 90% of the time. We don't know what P is yet. We're just going to play with the idea and see what happens. This is where it gets a little bit clever. I want to calculate the average expected outcome. This is a bit like saying, imagine every time there's a 1, that's a win for Prof. Let's assume that you get paid. Let's say that Noob gives you $1. And every time it's a -1, you lose $1. And if it's a 0, no one has to give anybody any money at all. Now, in a single game, you're either going to win or lose, or nothing happens. You win $1, you lose $1, or nothing. But over the course of a number of games, sometimes you'll win, sometimes you lose. The average expected outcome is saying if you play 10 games and you won $3 overall, your average expected outcome was 3 divided by 10, 0.3. You get like 30 cents per game. That's your average win rate. And that might be a useful number to use because that's the thing that Prof wants to maximize, because he would like to win as often as possible. That means the average amount that he wins needs to be as high as possible. What we can do here, even though we don't know what Noob is going to play, is to look separately at the two different things. If Noob plays scissors, then what do we end up with? Well, every time we play scissors, we get a draw, which is 0. But every time we play rock, we win $1. So if we play rock 20% of the time, we win $1 20% of the time. And our average expected outcome is 0.2, 20 cents per game. However, if Noob plays paper, then every time we play scissors, we get a win. So we get $1 for every time we play scissors, and we lose every time we play rock, which means we lose $1 the rest of the time. This gives us relatively simple looking algebraic expressions. One of them, 1 minus p, looks like it's going to get worse as p gets bigger. So the greater the chance of us sticking with scissors, the lower the expected outcome is going to be. But the other one is the other way around. If we make p bigger, then we're going to do better. So there's a trade-off between these. And of course, we can't just make p equal to 0 or equal to 1, because then we will be hanging all of our hopes on what Noob ends up doing. If p is equal to 0, then we do well if Noob plays S, but we do badly when Noob plays P. And the opposite happens if P is equal to 1. We can't just do the same thing every single time. But what if we make it so that the outcome is the same for both? We can do that algebraically like this. We say, when are they the same? Put them equal to each other, rearrange and solve, we get a number, 2/3. In order to make this happen, we have to play scissors 2/3 of the time and rock 1/3 of the time. But how, what have we even done? This Why would we want to make them equal? What's the point of that? Surely we're trying to win as much as possible. What's the advantage of saying let's make it so that it doesn't matter what noob does? Well, to illustrate that, we're going to use a graph. This is a graph that indicates the payoff depending on what our opponent does. So the first thing to notice is the numbers from 0 to 1 along the sliding scale. Those are the values of P. That's the probability that I choose scissors. So if I definitely choose scissors all the time, I'm all the way over to the right hand side at 1, and I either get a draw or I get a win, depending on whether my opponent goes with scissors or they go with rock. The purple line shows me the line I need to use to look it up if my opponent plays scissors, and the orange line is the one I look up if they play paper. If they play paper and I've played scissors, then I win. If they play scissors and I've played scissors, then it's a draw. So obviously very different outcomes depending on what my opponent does. And also very different but opposite outcomes if I make P equal to 0. If I'm all the way at the left hand side, then I'm really hoping they play scissors. But if they play paper, I'm screwed because I've just lost. The sweet spot is somewhere in between. We're aiming for the top, because an outcome of 1 just means I've won the game. An outcome of -1 means I lose every time. An outcome of 0 means a draw. So I want to be here. Why? Well, because I'm trying to mitigate the effect of not knowing what my opponent is going to do. Sometimes they play scissors, sometimes they play paper. A good strategy here is something that you might do when you play chess. You assume the worst. You assume that your opponent is going to play the very best move they can, which will be the worst thing for you. It might feel like a negative way of looking at life, but if you assume the worst, then you're unlikely to be disappointed, because chances are what happens isn't going to be quite that bad. Or at the very least, it won't be any worse than that, because it's the worst thing that could happen. So if, for instance, I go with 0.5, the worst thing that can happen is a draw, on average at least. It doesn't mean I'll never lose. It means that on average, over the period of a number of games, the average outcome is going to be a draw. So I could do that 50-50 approach. But that means on average, I get a draw if noob plays paper all the time, and I get a bit of a win if noob plays scissors. And if noob figures this out, they're very quickly going to start playing paper, and then I just get a draw every single time. If I don't want them to have any kind of say over the kind of outcome we get, I need to find the crossover point between what happens when they play paper and what happens when they play scissors, so that whichever one they choose, I don't care, I'm getting the same outcome. And that happens at the sweet spot where they cross. Imagine if I could choose a value for P, and then you could come along and decide which line I get to look it up in. Well, you're going to choose the line that gives me the worst outcome. If I choose 2/3 for my value of P, then it doesn't matter which line you choose, you're going to end up in the same place. The question now is, what does it mean to say my outcome is 1/3? We play scissors 2/3 of the time, we play rock 1/3 of the time, but what does it actually mean to get an average outcome of 1/3? Well, it means that if you play lots and lots of games, and you get a point every time you win, you lose a point every time you lose, then your average winnings are 1/3 of a point per game. You play 30 games, you'll probably get 10 points because you'll earn 1/3 the number of points compared to the number of games. That doesn't necessarily mean that you'll win 1/3 of the games and you'll draw the rest. It might mean you win 2/3 of the games and you lose 1/3 of them, but on average it works out the same. This diagram might help to make sense of it. If noob decides to play scissors all the time, then my strategy gives me a draw 2/3 of the time and a win the other 1/3 of the time. If noob, on the other hand, decides to play paper out of desperation, then I'm going to win 2/3 of the time every time I play scissors, but I'm going to lose 1/3 of the time whenever I play rock. So the fact that I have this ratio working out equivalent means I don't care what my opponent plays. The overall profile will look different, but not the overall points total. If they play scissors, then I'm going to win 1 and draw 2, and if they play paper, I'm going to win 2 and lose 1. So it's more volatile, it's got more variation I suppose with the paper version, but I still end up on average, if I get $1 every time I win, for every 3 games I'm going to be up $1. So what about our poor opponent? Whoever happens to be on the back foot in one of these exchanges, which in this case is noob, what can they do about it? What if you're that person? Because half the time when you're playing this game and you get into this scenario, you'll be on the other side. There's no magic choice of pair of values that's going to automatically mean you'll be on prof's side and you can guarantee a 1/3 chance of winning. So all you can do is do the right thing, the savvy thing, when it comes around. But when it's the wrong way around, what can you do? Well, nothing. At least if your opponent is playing optimally. If your opponent, like prof, has decided to do the savvy thing and switch intelligently between them, then there's nothing you can do to stop. In fact, I suppose it's a bit freeing, because there's nothing you can do that's going to make it any worse for you, and nothing you can do that's going to make it any better. Except if you don't play a perfect strategy yourself, your opponent might notice and start to exploit it. If you are always doing the same thing regardless of what they do, they're going to spot that and they're going to start playing whatever exploits what you're doing, potentially. So if you want to be on the safe side, regardless of what your opponent is doing, you've got to follow your own mixed strategy to make sure you minimize the amount you lose. Now it turns out you can do the same kind of process that we've just done for the other player. The difference is you're looking at your outcomes. So a 1 is a win for you and a -1 is a loss for you. It's just a reflection of the graph we've already seen. It turns out the best thing you can do is also the same thing as the best thing prof can do. You choose, with a probability 2/3, the thing that you both had in common, in this case scissors. One of you's got scissors and rock, the other one's got scissors and paper. Each of you, to guarantee this 1/3 payoff to the person who has the advantage, it needs to choose scissors 2/3 of the time. Now, it doesn't make his losing position a winning position. It doesn't automatically give him an advantage, but what it does do is minimizes the potential for loss. So if you know you're going to be losing, you make sure you lose as little as possible. This is what the payoff looks like if both players are wise to this strategy and they're both using optimal strategy. It now means that we don't care what the other player does. It does mean that on average the dominant player is going to win 4/9 of the time and draw 4/9 of the time and lose the rest of the time. I ran a few simulations so you can get a feel for just how much variation there is. For 100 games, there's not a whole lot of variation in here. You can see pretty consistently we're winning or drawing almost all of the time and only occasionally losing if we're following this strategy. Now I know that's kind of bad news for the person who's on the losing side of this, but remember, if you're following this strategy, then you minimize your losses when you're on the losing side and you maximize your wins when you're on the winning side. So now we've proved what the mixed strategy optimal scenario should be. How do you do this when you've only got a few seconds to decide? First, remember that all three of these are equivalent. You don't have to memorize a whole sequence of different random strategies. Just remember that if there's an overlap, your optimal strategy is to go with whatever you have in common 2/3 of the time. If you're the player who could beat both of your opponent's possible choices, you're the one who's probably standing to gain, on average, 1/3 of a point per game. But even if you're the other one, the optimal strategy is the same. If you see all the three options between you both, in other words, you're not looking at the same thing or the other person hasn't played the same thing twice, just choose the one that you have in common 2/3 of the time, choose the other one 1/3 of the time. In summary, how do we make sure we're playing this optimally to maximize our win percentage? First rule, never go with two of the same thing. It's a daft thing to do because the other player will probably be able to beat you, and even if they don't beat you, they're going to get a draw. Number two, if the two of you end up picking the same thing as each other, which will happen from time to time, it's going to be a boring match, but as long as you pick the option that wins, then you'll be just fine. It guarantees a draw. You're probably not going to win, but you're also not going to lose. And number three, the most important, the one that was the most subtle, if you both pick different things, go with the one you both had 2/3 of the time. So in this scenario, scissors is the one that you've both chosen, so pick that one most of the time, pick the other one about one time in every three. Ideally, I'd say grab a dice. You can roll yourself a dice, and if it comes out as a 1, 2, 3 or 4, you go with scissors. If it comes out as a 5 or 6, you go with the other one, if scissors is the thing you had in common. And that's it. Remember that this version is the same whether you're the dominant player or the other player. You're either going to minimize your losses or you're going to maximize your wins. Give it a try, play it against some people, see if you end up coming out on top.